groups work on this.
Yeah. Okay, so good morning. Online participants, we are starting now. So before we look at the solver, we already need less details now because we have already finished 4 days of workshop and we have good knowledge of all the NSM solvers. So I want to show you something now that you know that these codes are all supposed to be for supercomputers. I want you to be aware of this particular website where you get to know about supercomputers across the world. As I saw top500.org. It is a site that is updated 2 times a year, and you get to see what is the fastest in the world and where are the top systems. So Frontier is the one which is an Oak Ridge National Laboratory, and it has the record which the ACM Gordon Bell Prize is actually awarded to. So they are the ones who run the code basically. Now, if you look at statistics, I want to show some statistics which help you to prepare yourself to start using these resources. So one of the first things I want you to see is this one, operating system. Okay, which operating system is running on the supercomputers across the world? Okay, now if you see the result is 100% Linux. Okay, so which means that you have to start learning Linux if you want to do any supercomputer. There is not even one supercomputer that runs anything else. Okay, so this is very clear message. Now, which type of the Linux is also not very important because you have actually Ubuntu also present. Okay, so which means that if you are using Ubuntu Linux on a laptop, that is already quite popular and it does work. You can see that many of them did not disclose what type of a Linux, but CentOS, Enterprise Linux usually is very common. You can see from the red, it is Cray Linux, okay, and then the other one, slightly bigger one, okay, is Red Hat. So in our institute, for example, that would be CentOS. Okay, so you can get to know these things. Particularly for us in India, we need to also look at where are we. Okay, we have to improve. Okay, you can see that the systems are which are fastest in the world. It's basically US, China, Germany, Japan, and all. And India is at 20th position. So we are number 1 in population and only 20th in supercomputing. That is really very sad. We have to improve. The only way we can improve our position or status is by learning how to run our solvers on supercomputers and solve bigger problems. And thereby, when the hunger is there, the government will definitely fund to satisfy that hunger and put up more systems. Automatically, that will happen. As of now, the number of users who are able to compile and run their codes on a supercomputer with scalability is very limited. Many of the people who do computation use commercial softwares on some desktop machines and they are happy with it. So the only then when we change from that scenario, we can improve. You can see that yesterday's professor who has given us talk, Professor Wu from Taiwan, they have actually such a small island, but they have more supercomputers than all of us here. So this is something that I want you to have at the back of the mind. Okay, all of us need to do something about it. So learning Linux and starting to use programs that can be compiled is a very good step forward. Okay, so this is the something I wanted to just show. I will just close this tab. I will need that now. Okay. So now let us get back and see here. We will see if I can do control L. Okay. So I will give you details which are about what will run on GPUs because now already you are aware that GPUs are going to be very powerful and they are good. So I am going to give you some inputs on that more than the phase field because phase field already we have started to use. I will just show what is possible with OpenCL solvers that we have. So you get motivated to start learning how to do that. Okay. So this solver is originally developed by Gerald Tennyson as a part of his PhD, and that was for a binary system. And then Mohan extended that for multi-component system during his PhD. And then, of course, during postdoc and while working at NSM, he has extended it for multi-phase, and therefore now it's benchmarked. This solver has been benchmarked for the dendrite growth with the grand potential solver as well as the one with open form. So we can say that all of them are benchmarked to give the same results. During the development, we have had some good support from Rupesh, who's the HPC person from Institute. He was in charge of HPC. He had his own cluster that he allowed us to run. So 16 GPUs at one time we could not try anywhere. So he was the one who offered it. And then we also had one interesting case I want to mention. When we first ran it for AMD processor, we got about 2.4 teraflops on a single card, which is only about 30,000 or 40,000 rupees. So AMD was very interested by that, and they showcased our work as a part of HIPC in Bangalore. And then they also gave us an account in their center in Singapore, where Mohan could run the code on 16 GPUs to do the scaling study. So that was a time when the GPU cluster was not yet available on the campus. So that was something that I thought I should mention. So these are all benchmarked and scalable as we have done earlier. So today, if you see most of the places where we have HPCs, maybe in IGCAR or DRDO or many of the IITs and academic institutes, we will have clusters that are basically heterogeneous clusters. Most of them are heterogeneous clusters where you have got multiple CPUs, and each of the nodes will have several cores of the CPU and also a GPU. Okay, one or more GPUs. So our programs have to be such that they can take advantage of the heterogeneous cluster. Okay, and then you are able to then do things that are much higher scale. Okay, so our solvers, MicroSim solvers, are ready to attack all the three types of clusters. They can do all of them. But for heterogeneous, there is a lot of challenge because you have to communicate across the nodes using MPI, and then you have to communicate with the GPUs using either OpenCL or CUDA, and then together you are supposed to distribute the workload, and that's something that is already established in our solvers. And as you have seen yesterday, AMREX would also do this quite elegantly without too much of low-level knowledge of the architecture. Okay, so some skills that you need to pick up in the next few weeks. Take your time to do that, but you should pick up these skills to make the best out of the MicroSim accessibility. That is, learn how to use a terminal very well. Bash should be very comfortable to you. Bash commands to write files and then copy them across, zipping them and pushing them across. All of that you should be comfortable. Then SSH and SCP, that is to log into a remote shell and then to copy files from a remote location. That you must be familiar, because most of the time you cannot sit right in front of a supercomputer. It will be only available through a IP address. That's all you will have access to. Okay, so learn to do that. Sometimes you may have to do that over the VPN also, but that's not a very difficult thing. VPN is a separate application. Once you switch on, you basically have an address that allows you to communicate. So if you learn how to do SSH and SCP from a terminal using Bash, by and large, you are equipped to make the best out of the supercomputing. Now, there are a lot of files that we'll be creating. These are going to be large in number. You cannot actually zip all of them and download the single file, because the network connectivity may not be assured for so long. We are talking about several tens of GB of data that will come finally. So rsync is also one possibility. You can do rsync over SSH so that the files can come one after other. So each single file may be just 1 or 2 GB, that will come quite fast. And then even if the network gets cut, the rsync will ensure that you are not duplicating the file transfer. So it will actually get part of a file also. You don't need to worry that the file has been transferred only part of it. So rsync is something that we must be familiar. Now wget is again a different way of getting files. Let us say you have a very big file that you have to get from some institute, and the SSH or a secure copy is always stripping. It is not finishing. Then it's a very good idea to learn that in the institute where the large file is located, find out if they have a website, some website that you are having access, put the file in the website, and then using wget, you can pull over the internet, because wget can continue getting the file whenever it is broken. Okay, it will keep on continuing. And once the file has been completely gotten, you can remove it from the website. No need of any password, etc., because the location of that file, the file name, etc., has not been given anywhere in any index. So nobody will know that such a file is there. And by the time you finish the transaction, you remove, then even if somebody wants to find out, the file has gone removed already. So there's no security problem. And even if they have the data, I mean, they don't know what to do with it because they don't know what is there in the file anyway. So don't worry. So try to find these arrangements as you work around so that your experience of working with large amount of data and big domains, etc., is possible. That's exactly the power of MicroSim. Please remember that to run small 2D simulations, there are many things available. But to run 3D large scale simulations, MicroSim is having a unique capability. So these skills will help you. Now, text editors also should learn how to edit a text within the terminal. VA editor is my favorite. You can also use Nano editor, which is very, very easy to do. The reason is that you have to submit some jobs on the scheduler on the supercomputer. So some commands or some options need to be changed. So it should not be that you are changing it in a notepad here computer, then copying it over to the terminal on a remote location. It should be such that you can open the editor within the terminal and edit those things, and that capability is very important. So please learn, okay? And of course, VPN and all those awareness should be there. And one of the reasons why MicroSim will initially maybe a bit difficult for you to learn, but after that it suddenly becomes very, very powerful is because there is no issue of licenses. There is no site license or a node lock license, USB dongle, authentication, subscription, nothing. Okay, it's just free and available for you. So you start seeing that benefit only when you start using. So to compare that, I will tell you that if you want to do, let us say, a commercial software, FEM commercial software, I don't want to mention the names, but the license costs when you want to run on HPC with hundreds of cores, license costs come into crores of rupees, crores. And suddenly you see that all the money is disappeared just when you are trying to even do a simulation. So you will start benefiting only when you do big scale simulations and compare the cost. Many of the commercial tools available for microstructure simulation are such that you can't even do such simulations. Okay. Now, what are the various paradigms that are available for large scale simulations? If you see MPI, we have already mentioned the open form based solver uses MPI on the background to do that communication. Amrex also uses MPI in the background. So MPI is one library that allows you to distribute workload across computers in a distributed memory system. And explicitly, you are telling what data should go and what data should be brought back. It's not very difficult. MPI library may be big, but you will need about 10 to 15 function calls for your life. You don't need more than that. It's only some 10 calls or 15 calls. So if you learn that, you may be able to start taking advantage of MPI. Okay? If you learn MPI, your program will be made much more scalable because you understand how the data has to be transferred. Okay? So it's very important. Now, automatic parallelization is also being done by OpenMP and OpenACC. Amrex does it on the background automatically. And we can also do it in our programs by giving some headers. However, in our solvers, we have not used it. Because anyway, we have been able to write MPI code, so we don't need these automatic parallelization because MPI generally is much faster or scalable than OpenMP or OpenACC for those who are knowledgeable about how it is going to be distributed. If you are putting that knowledge, MPI can be faster and more parallel. Now, coming to the accelerators like GPUs, the technologies that are there currently in place are the CUDA and OpenCL. Okay? So CUDA is a proprietary platform of NVIDIA. And it is not chargeable to you upfront, but if you look at the end user's license agreement, you could be charged at some point in time. Okay, you could be because it is not free as such. So therefore, one has to be cautious about that part. OpenCL, on the other hand, is a creation of Apple, and they actually donated it to a what do you call a foundation called Kronos. And they asked Kronos to maintain it and give it as a royalty-free platform for everyone. So it is actually a free platform. So if you develop a program in OpenCL and if it becomes very successful, you don't have to pay anybody anything. And OpenCL is also on many platforms. I will show you some details because of which it has also been adopted as a standard. So like ANSI C or ANSI C++, OpenCL also is a standard conformant language, which means all the vendors who support it come together and agree upon what features should be there, and then those features will be implemented by the versions. And the versions have come up to 3. Version 3 is available right now. Okay. Now from there, SYCL has come, where C++ programs can be written that can be automatically taking advantage of either OpenCL or CUDA, such that they can run on GPU. So I will show some snippets about what SYCL is shortly. SYCL is also an ISO standard. OpenCL and SYCL are also ISO standard. What it means is that they will be supported in the long term by many people. Okay. And the most successful implementation of SYCL is the so-called data parallel C++ from Intel compiler. Luckily, the compiler is free. Okay, and if you install one API, you can write SYCL codes and start taking advantage right away. One of the biggest advantages of OpenCL and SYCL is that you can run them on your CPU. You don't need to have actually any accelerator. You can run them on your CPU first. Then after the code is developed, you can then go to a cluster or a workstation with a GPU and try it out. Then you can see the advantage that is coming out to the accelerator. But code development itself, you don't need to have. This is unlike CUDA. For example, you cannot even compile and run unless you have actually GPU working on your machine. So there's a what do you call ability for everybody to start developing code in OpenCL and SYCL. Okay, so what is OpenCL? Because so the blurb that is available on chronos.org website is very instructive and very nice. You can say OpenCL is an open royalty-free standard. It's a standard. Okay, for class platform parallel programming. Okay, and diverse accelerator. Diverse. It works on practically every accelerator. For example, I have run Gerald's code on Intel Xeon 5 GPU, Xeon processor, i7 processor, then AMD Ryzen processor, and AMD GPU. Okay, and it ran on all of them. Okay. So definitely this I definitely agree that it is a platform for diverse accelerators found in supercomputers, cloud service, etc. And it also improves the speed, etc., which is true. For example, we have tried it on Xeon Gold processor, and it is blazing fast. Okay. So even though you may have only a 24 core CPU, you can run OpenCL codes on it, and it will run very fast. Okay. So you don't have to think that to do GPU programming you should have a GPU. Okay. You don't need to have it. Okay. And what is it used for? They claim it is used for scientific, medical software, vision processing, neural network training, etc. But let us see the tools. You will see that they are available. Okay. And you see that it is available also for FPGA. Okay, now this is a very good attraction. Field programmable gate array is a device that will come in future. Right now it's available, but we, that is engineers, except the electrical engineers, are not using it to the full capacity. But it will start making a big deal. Like right now GPUs are being put to use. I'm predicting that after a few years, FPGAs also will be put to use, where very complex algorithms can be made to work on the hardware, so that hardware speed can be accelerating your algorithms. If you want to start learning FPGA and start writing some algorithms, Intel DevCloud is available. You can log in there for free, and FPGAs are available. You can submit jobs and run and see and to do. Now, to buy and own it is a bit expensive at this moment. Okay, so FPGAs are very expensive devices. It is the same story as how GPUs were in the past. It will become cheaper after a certain time. Even neural network hardware also it can run. There are certain neural processors that are being created, particularly by Apple and Google. They will also run OpenCL. Okay, that is the beauty. Okay, even the neural processor also will run OpenCL. So if you learn how to run OpenCL code, you can actually do many things on this emerging hardware. So this is a list of all the companies on the top. Below the line are the technologies. You can see who all are using OpenCL, and you can see some logos. I will just alert you. PyOpenCL, Python library is available. SYCL itself actually uses OpenCL on the down. Adobe, all the graphic tools, beautiful effects that you are creating, etc. on the back are done by OpenCL. You see MATLAB also supports OpenCL, and so on. There are a lot of softwares that are there. Gromax, for example, again, you are familiar with that. And below are the companies' names who are all supported. A lot of companies. Qualcomm is there. Then you have got Intel and NVIDIA. All of them wholeheartedly supporting the OpenCL platform. So it's a very good idea to see how we can use it. Okay, so here is some certain screenshots I have taken from the Chronos website, and that is essentially for us to just get familiar with some words. So SPIR is one word I'm just alerting you. Okay, so what is the low-level language that actually runs on the GPU? Okay, so it used to be, for example, SPIR, and now you see that we have got OpenCL where we ourselves can write the code. In the past, if you wanted to write in a low-level language, it's a bit difficult. So you had a high-level language, then it should be converted to the low-level language, which should be written. Okay, so PTX is such a global language for NVIDIA, and we don't write in code in PTX. We don't. It's like nobody writes code in assembly. We write in high-level language, it gets compiled. So that is the story. But only thing is, OpenCL is such a way that it is low enough that it can run on the hardware, but high enough that we can write code on it. So it's a very nice kind of a intermediary. Vulkan is again one such intermediate language which was very popular on AMD hardware for a certain time. Now they're all getting merged with certain newer intermediate language representations. Now here again, I wanted to mention one more thing. So you would see that LLVM is one keyword I want to draw your attention. So many of the people who start developing these tools and libraries want to also provide a way by which you have ability to create compilers also. So LLVM is one such platform, okay, on which the compilers are available. So today you may ask, is there any C compiler that I can run anywhere in the world on any machine? Okay, yes, it is there. Okay, LLVM C compiler, C-Lang compiler is available for you. It will work on any machine. Okay, because LLVM is going to run on every hardware and you can run on it. So you have the C-Lang compiler running on LLVM, making code compilation available. So how do we write codes that even create drivers, etc.? They write using these kind of platforms. Okay, so you see that OpenCL is taking some advantage of C-Lang and is able to go all the way up to the SPIR, and SQL also does that via LLVM and go up to SPIR, and then the SPIR will actually then run onto the hardware. So like that, there are some intermediate layers that we are not directly aware, but we are only looking at OpenCL code or SQL code. Then eventually all these tools are available for you to run. These are all available as GitHub repos. So for example, C-Lang is available as a GitHub repo. You just core the repo and start using the compiler. You don't need to pay anyone for the compiler. They are all available for free. Similarly, there are the SQL implementations available on GitHub. Tricycle is one such implementation. It's available on GitHub. You can just for the repo, compile it, and then you are ready to go for developing the code on the SQL platform. Okay, now where are we with respect to the development? So you can see that it's now about 12-13 years that OpenCL has been moving. So you can see that we became aware of it at the right time. Okay, Gerald's PhD sort of was picking up around the time OpenCL came. So by the time it became popular, Gerald was able to at least use it. So we are just, if you look at the time, Gerald's PhD and Mohan's PhD, one after other, is overlapping with the same time frame, the last 10 years basically. So today we are having OpenCL 3, which is the latest version. Latest is 2020 version, and it is continuing even now. Okay. So go to Chronos.org website. You will see all these details available there with a lot of documentation, links, and all that. So again, some more points about the ecosystem. All of these actually allow you to write the code in either C++ or in C language, and they can be compiled so that they can run on multiple devices. So the OpenCL runtime will run on multiple devices. It will run either in SPIR 5 or OpenCL C. Okay, so it depends upon the hardware implementation. You don't need to worry about that. Okay. So SPIR is one intermediate form which will run, and depending upon the device, you don't need to worry about that. That part is taken care by the compiler. Okay, so what is SPIR is also just given there. Okay, standard portable intermediate representation version 5. Okay. Now again, OpenCL is a backend for many these technologies. and they are all listed here. OpenACC also has taken advantage of it, and WebCL. So WebCL, for example, you are watching a program on the browser, and the browser has to show some rendering which is very sophisticated. So the browser itself does not have capability to run too much. It is only having capability to run a JavaScript. That's all. But can it still render something very sophisticated? Answer is yes. It can do some computations because it will render via OpenCL driver. It can actually use the graphics card to do some computation. Okay, so browser running something like a program on your CPU is a very tricky thing. It's not very easy. It's a client-side computation. Client-side computation is very difficult for us to launch via the browser. Okay, but it can do through certain technologies, and this is one such way by which you can do. So maybe in future we may have some scripts that will be written such that on the browser people can click, and some of them are running on the client's machine, not on the server. Okay, so those things are also possible once we learn OpenCL very well. Intel has been very wholeheartedly supporting OpenCL. Their hardware supports OpenCL very well. They run very fast, and they have developed compilers for it, drivers for it, runtime libraries for it. Okay, so if you buy Intel hardware, you are in very good shape. Intel what is called as runtime library for OpenCL is readily available. You can download it for free, and then after that, any OpenCL code that we are having can be compiled and run, and that runs very fast on many of those processors, particularly the Xeon series of processors. And they have given even the debugging tools and code builders and studios, the IDEs, that integrated development environments, etc. So all of them are available, and they allow you to even try them out for free on Intel Dev Cloud, and then later on you can install them on your own laptop and try them out on your machine also. So you have got abilities to do both of them. So Intel has been very strong supporter of OpenCL technology. How can we run that? Okay, so you only need this much. Okay, that is, while compiling, you need to tell what are the headers, and while running, while linking to make the executable, you need to link the OpenCL library. These are the only two things that are required for OpenCL. There's nothing more special. Okay, nothing more. So GCC compiler itself can actually create your OpenCL solver to run. GCC. Now we are actually trying to do with Intel because it is a bit faster, but GCC itself can also do that. And the third point is where you need to be a bit careful. The GPU may or may not be visible to you depending upon your video group, etc. So one has to watch out, and if you are able to get this visible, then you are ready to take advantage of it. How do you check that the GPU is available for you? Is using a tool called CL Info. So there's a tool called CL Info. You can install it using apt-get and run it. If CL Info throws on the screen what all the GPU devices it detected, that means you are ready to start using them for your work. Okay, so check it out and try them out. That is what you have to fix first. Once that is fixed, your OpenCL computation possibility is ready. Okay. How does the program look like? The program actually assumes that the GPU or the accelerator is having certain architecture. Now remember, it is CPU or GPU, doesn't matter. Okay? It assumes that there is something called a global memory for the accelerator and also local memory for the individual work elements. And there are many work elements. And there are so many that you have to inquire the accelerator how many are there. And if you run a loop from I is equal to 1 to 1000, it is possible that, let us say there are 100 work elements, then 100 steps of the loop are running simultaneously. And in, let us say, in 10 such cycles, the loop is over. Okay, that is the capability of the architecture. The architecture is imagining it's like that. Now, how does it actually work on a CPU? Well, CPU has the ability to do multiple cores. It has already, let us say, if you take Intel Xeon processor, it has 32 cores, let us say. So that means that it is assuming that 32 work elements are possible readily. Now, there is also a concept of pipelining. That is, it will give you double the number of cores if you enable that switch. And therefore, that many number of loops of the that many steps of the loop can be done simultaneously immediately. Now, the memory, it is assumed that there is a memory for the accelerator. Now, in reality, what will happen is that if it is an actual GPU, like AMD card or NVIDIA card, that is a memory on the card. And if it is a CPU working as an accelerator, it is the same RAM. Okay, so you don't need to worry about that. However, always remember that that is not the same as global memory. That is RAM. Pretend that it is not the same as RAM. So therefore, what you should do is whenever you are trying to get an array computed, you have to make a call to send that array to the GPU and get it computed. And if it is a CPU that is running, it is just going from one part of the RAM to another part of the RAM. That's all, and it will be very fast. If it is a actual GPU like Intel or AMD or NVIDIA card, it will be going via the PCI bus onto the memory of the card. It will travel quite a lot. If you go, it is going from the main memory module through the PCI bus and onto the memory of the card. And therefore, it depends upon the motherboard capacity also, how fast it can be. Today, the AMD motherboards have come up a very big way, and they have a bandwidth of several hundreds of Gbps. Okay, so we have very good speeds that are possible on PCI. Version 4 are available with the cards to be put. So blazing speed is there. So it's not very expensive for us to do. Now, our programs, the way we have written is such that you don't need to send the data again and again. Okay. Now, how often do we need the data to come out? We need it to come out when you want to print it. No. Let us say the phase field variable. When do we need the variable in the main memory on the CPU? Only when you want to write the file. Until you want to write the file, you don't need to bring the data. So you can send the data to the GPU, let it perform some 1000 steps of computation, and then I'll get one copy to write to the file. So which means that we can already optimize the communication to be very minimal, and that has been done. And that's the reason why these solvers are actually performing very well. Now, some of these communications can also be automated in the case of NVIDIA library and CUDA. Okay, they can be automated. But in OpenCL version 3 has that what's called unified memory concept, and it can be automated. But we have not done that. We have assumed that we are only going to transfer the data. So we do it very sparingly. So we don't need to worry about the scale up. Scale up is guaranteed because we do it sparingly that we do. So the various steps that are there in OpenCL program are listed here. So you initialize the domain, allocate the memory for the data structures, perform the IDs, that is ask what is the unique ID of the CPU and GPU, create the context. Create the context means basically preparing the environment for you to run, and then make a command queue. Command queue basically is trying to tell what kernel is going to go into the work element and run. The kernel is basically a piece of code. And all our solvers are written as kernels. So each kernel will go and work on one stencil and perform the computation. Okay. So this is a decision we took very early in Gerald's PhD thesis. We took the decision that we will not run on an array. We will actually make the array calculate stencils, and we will give stencils to the kernel and let the kernel run for each stencil independently. Okay, that's a decision we took, and it was very, very fruitful because now our solvers are very scalable. Okay. Now we do some memory buffers, read and write, etc. Then we'll queue up the various buffers for the transfer of the data. And then the kernels are written in .cl files. They are actually C programming languages. So that can be read and then set up the kernels for execution. This is how it works. And when everything is done, you flush and close the call so that the GPU is now available for others to run. This is how the program is going to be done. Now I want to tell you why it is very important for us to be good in programming. You cannot debug a C language program code running on GPU. You cannot stop it halfway and tell what is happening. So you have to do it on CPU first, ensure that your logic is running correctly. Then you make some headers that are different for it to run on the kernel and send it off to the kernel. Okay, so you have to be good in writing the C language if you want to write a GPU, because you cannot actually debug the C kernels. You cannot debug the kernels easily. Okay, you have to actually make them run on the CPU, debug them, make sure that they are working correctly. There is no numerical error at all, and then pack them up as kernels and send it off. Okay, so you cannot start learning programming while you are doing GPU programming. You have to learn programming, be good at it, and then after that you do GPU programming. Okay, it's a harsh fact, but that's how it is. But don't worry, because in MicroSim, all the programs are already written, so you may not need to write much code. Okay, all the solvers are already made, so you don't have to be afraid of it. You can start running them automatically. So these are the various calls that we have used. You can see there are not many. about some 15, 16 calls. These are all the only functions that you need to know if you want to learn OpenCL programming for the solver that Gerald and Mohan have done. Only these many calls. It's not a very large number of programming calls that are required. And how does the code look like? Code looks like a C language code only. You can see it. Okay, the code is available to you. MicroSim repository is available to you. You can open the CL files and have a look. They look very simple. They are having the way the code is written. It's just C language code only, except for some small keywords that are required for us to do. Okay. Now optimization is necessary. We have done the optimization. Okay, so the code that is being given to you is already optimized for speed up in such a way that it maximizes the throughput from the GPU. So that work has been already done. Both Gerald and Mohan were pretty good in these kind of tasks. In fact, there was one such tool called Alinea for debugging and optimization. I can proudly say that at the time, these are the only two students who could actually run it in the whole campus. There was nobody else who could run that tool. So people used to come to them to ask how to use the tool. Okay, so they were so good and they have put it to good use and made the code optimal. Okay, so all the optimization has been done. Optimization done along these kind of aspects that I have told: vectorization, data alignment, data layout, as well as the control flow between the work items. Okay, all of that has been taken care. Okay. Now, whereas the tools are using OpenCL, the reason I'm mentioning is to tell you that maybe you are using OpenCL without knowing it's possible. Okay, so Altair tools are very popular among mechanical simulations, structural analysis. They actually have OpenCL solver. Big DFT, we have talked about it on one of these days. Okay, Big DFT also uses OpenCL. So Autodesk is very popular. They also use OpenCL. Dassault System Simulia, Abacus, has OpenCL on the back end. So what we have to do is some of these which are actually capable of running OpenCL. If you find a good hardware with a very fast OpenCL accelerator, it means that it's not only for this commercial software, you can also use it for your program. Okay, that's the advantage. Okay. Now, some of the simulations that were done by Gerald and Mohan are shown here. So such a very rich dendrite formation as well as good scaling with respect to the number of GPUs, etc. All of that is done. And the first paper was published in 2014. You can see 2014 versus when it was started, 2009, as OpenCL started. So within first few years, we have our paper that is already there. Okay? And whatever is there in that paper, you can do it now with the solver. Okay? So it is already available for you with that capability. So the equations, they look very similar to what you have seen already here. So this is actually KKS model, the same model which I think Shashwata also has described about it. It's the same KKS model. And there also we had a discussion about anti-trapping term. Here also the JAT, the anti-trapping term. Abhik has already explained to you about that. So the formulation wise, it is having lot of overlaps with the different solvers. So the KKS part is one overlap. The anti-trapping part is another overlap. Okay, and the anisotropy already again we discussed about it in yesterday's session also. So that is also modeled in a similar manner. So all of them have very similar kind of formulations. The PhD thesis are now publicly available on the National Digital Library in IIT Kharagpur. So if you search for Mohan's thesis, it is all available in public domain. The PDFs are available. So you can download and see the derivations that he has put in place. So you can get all the details about the models that are there in the code. Okay? So all the theses are available. Both Mohan's and Gerald's thesis are available publicly. Okay? Implementation, we have gone only up to the 27-point stencil for isotropic Laplacian to be implemented, and that is sufficient for us to avoid grid anisotropy. And two geometries have been implemented, which already discussed in the front end: the free dendrite growth or free solidification and directional. Okay. So for those who are working in additive manufacturing, welding, and casting, etc., the free solidification, the direct solidification is sufficient. You don't need to go more than that. And for those who are working on only casting or spray forming or droplet solidification, etc., free solidification on the first top domain is available. So if you learn how to give boundary conditions for these two cases, it is sufficient for most of your work. So don't think as if you have to keep on learning various boundary conditions. It's only 2 boundaries, that's all. Okay, most of the time this is sufficient for us. Okay, and the way it is split is by slicing the array. Already we have decided to slice only in one direction. Okay, only linearly we are splitting, that is enough. Okay, and so if you have 16 nodes, it will be split into 16 parts. That's all. It's not by 4 by 4, it's by 1 by 16 basically. Okay, and that is a decision that we took because of minimizing the communication, the ghost cells, etc. Yesterday's Amrex the discussion, you already understood what is called a ghost cell. Here, the ones which are colored in cyan are basically the ghost cells. They copy the data for the neighbors at the boundary, and then that copying is taken care in the communication. All the communications already know which way have to be done copying, and that has been taken care. Okay. And some work has to be done on the CPU, some work has to be done on the GPU. That also has been divided properly. Because it's not as if every simple calculation has to be done on the GPU, not necessary. The CPU is very fast. So we have divided the task in such a way that only the solver to update the phase field variable and composition variable are running on the GPU. Everything else, bookkeeping, stencil making, all of that is run on the CPU. So we have divided the tasks in that sense and already optimized about that. Okay, and we have also taken certain advantages of some of the features that are emerging. So the code also started to use newer and newer features as we went along. So for the OpenCL, most of the new features are available. So I suppose our code, when we are compiling, it is running very optimally on the intermediate level also, because we are getting more than 50% of the rated capacity of the card. Okay, and if you get half the rated capacity, that is theoretical capacity, that is already very surprising for many people. Okay, because even 10% is actually built in. Just like people say, what percentage of our brain do we use? People say only 5% of the brain capacity we use. That's already too much for some people, but that's true. So same thing with the CPUs also. You're using already 50%. That's great. Okay, so it's already optimal. Okay, and it has been implemented in this manner. I will skip. We already talked about that. So here I want to tell one more thing that you have to get here. So of course, the publications, we have not done many publications, but we have done a lot of care in writing the code. I want to tell you here. So Mohan, what he has spent time is to understand that when there is a data transfer, the data transfer is done independently in the hardware than the computation. Computation is done by the work element. Data transfer is done by the memory. Therefore, they can be done simultaneously. Okay, it's possible to do simultaneously. So what Mohan has planned the calls is the data transfer is done in what is called a non-blocking mode. That is, the data transfer is initiated, but you don't need to wait for it to finish before you do the computation. So while the computation is happening, the data transfer is also happening. Okay, and then he will check whether the data transfer is over before he goes to the next computation. By then the data transfer is over. So he has already done the calculation if how many work elements are good, so that this kind of a parallelism is possible. It is something like when I want to transfer items, I can do like this. While I am putting with one hand out, I can also do the same thing. I'm doing two things at the same time. Okay, so that is what it is happening. The IO, that is input output, and the computation are basically happening simultaneously in the GPU. That's the reason why we are getting the speed. Okay, so it took a lot of effort for us to reach that understanding and implement it. And today you have the benefit that is already available for you in the solvers. Okay, so this is how he has analyzed the debugger is able to tell what is happening, and then therefore you are able to do this kind of a analysis. Okay, so read-write operations are optimally placed in such a way that it is giving overall speed. Okay, so you can see the screenshot up that is coming from the debugger. Okay, by understanding the debugger only, he is able to do this optimization. Okay, and he has done both the weak scaling and strong scaling already. I think I think Tanmay was showing that. Okay, so both the weak scaling and strong scaling has been shown, and we are already confident that for pretty large sizes, it is quite scalable. More than 16 GPUs, we can go. Okay, and it's always that when you go to larger scale, you should also go for a larger problem. Then only the communication becomes small enough that you can take advantage. Okay, you cannot say I want to run only 4000 by 4000, but on 1000 processors. I mean, it's a waste. Why do you want to do that? Okay, if you want to go for 1000 processors, do something big like 1000 by 1000 by 1000, something like that. Okay, so please take care of such limitations to take advantage of that. So what kind of results are possible? These kind of results are readily possible, immediately possible for you that you can take advantage of. Okay, so the interdendritic spacings and the segregations of the dendrite for multi-component alloys is readily possible. These have been already benchmarked. Okay, again, I was asked by some people earlier, even Professor Wu has asked me, saying, did you benchmark? The answer is yes. We have actually done the additive manufacturing samples, done the composition analysis and benchmarked. So we know that these results are very, very reasonable. So very close to reality. Okay. And these also are capable of producing really very beautiful dendrites. So Gerard has produced one beautiful dendrite with multi-contours. Mohan also has produced this. This I really like. You can see the number of grid points. It is a huge number, 10 to the power of 10. 10 to the power of 10. Okay, that's a huge number of degrees of freedom. And into 5, because elements are there, okay, and into million time steps. So you can then see how much of the computation that is. Okay, so this what do you learn from this? Okay, I want to tell you, if you see here the orange color surface, look at the orange color surface. It is interconnected in multiple dimensions. Okay, what that implies is in 3-dimensional space, the solute field is interconnected. So the diffusion process is such that it actually takes place in 3 dimensions. So if you actually do a simulation only in 2 dimensions, you may not get the complete picture. You may actually get a little bit odd results because sometimes you may say solute cannot go this way, but it can go around. So because you missed out the other dimension, you may think that the diffusion process is not happening, but it may actually happen in reality. So ability to do 3-dimensional simulation is a very important for us to get the processes correct. Now, obviously, to do 3-dimensional simulations, you need a tool that actually works fast and efficient, and MicroSim will be able to do that. Okay, I think Soma also remembers trying to do 3-dimensional simulations using the commercial software, and it's very difficult, right? Yeah. So it takes several days to do. This actually runs in within about a day to give you a big rate. Okay? So when Gerard started, he estimated that he will need about 3 months to finish a simulation. And by the time Mohan finished, he was able to bring down to just few hours using multiple GPUs. And that's a very big step. So today you can do it in just few hours of multiple GPUs. If you have one GPU, for a day, you can get a pretty good result. It can also give you the 3-dimensional view of the solute transfer, and you can relate to it the 3-dimensional microstructure evaluation in additive manufacturing very nicely, and you can actually then compare what is happening in actual experiments with what is possible using computation. Some of these are also benchmarked even in the 3-dimensional space. The segregations that are there in between the cells are the ones why the detrimental phases can form. Okay, Lavie phase, okay, and TCP phases, etc. will form. So how much segregation is necessary to form that phase is also possible for us to estimate using the so-called JMAT Pro calculations. We can estimate. Now here is something that I again want you to pay attention. The curvature effect is the reason why the segregation is more. Okay, whenever there is a curvature, the solute segregation is more. Okay. Now, if you look at 2D versus 3D, in 2D, the curvature term has only 1 by R. In 3D, it has 1 by R1 plus 1 by R2 as a curvature term. So the 3D space is much more curved than 2D space. If you took a cylinder versus a sphere, okay, if you look at a sphere, it is curved this way and also this way. Whereas if you take a cylinder, it's only curved one way. So which is having more curvature is going to throw more solute through the Gibbs-Thompson effect. And therefore, your predictions on the phase formation in the interdendritic or intercellular regions are going to be closer if you do 3-dimensional simulations. If you do 2-dimensional, you may not get them correct. The number may not be close enough. 3D, if you do, the numbers will be such that if you run a JMAT Pro calculation, you will see that it's very reasonable for the TCP phase or a delta phase or a Lavie phase to form. And then you can go on to do experiments to check it is true. And here in this case of niobium containing materials, the Lavie phase formation has been shown and we have benchmarked it. Okay. And under what temperature gradient and cooling rate you can avoid it also, we have done it. And that is Rahul's paper, separately he has published. Okay. So both of them can be looked at. So these are all what are possible for you. And of course, you can change the system. You can go to some other alloy system, etc. That is all up to you. Okay, but it has been benchmarked for nickel-based super alloy is quite well. Okay, and 7 elements. Inconel 718 alloy composition, complete alloy composition has been solved using the same MicroSim solver, and that is what is the result in Mohan's thesis. Okay, so for 718 alloy, the segregation has been solved without any approximation, and the results are available in Mohan's thesis. Okay, so with that, I wrap up, and I'll just mention some few points about sickle, just an advertisement. We don't have it released yet. Chirantandeep is writing some codes, and we will plan to do some more development as we go along. So I'm hoping that in the upcoming releases of MicroSim, we will have a sickle solver also possible. So what does sickle promise to do? Sickle promise you to write in such a way that it is across multiple intermediate representations. Okay, multiple intermediate representations for you to be able to run. Okay. And that is a very, very big promise. And right now, Intel is already showing you, but they are promising on any CPU, any CPU. And you can look at the Vulkan, MLIR, MPI, okay, VEO. These are all basically intermediate representations that they will be able to put on various hardware later on. And it is also running on Xilinx FPGAs already, apart from just OpenCL platforms, Spear, etc., which are already running on all CPUs and GPUs. So sickle promises that if you write once a code in C++, it will run everywhere. Okay, that's a promise. It is developing. It is happening now. For example, 5 years back, there is no sickle. But it's now there. So it will happen. So 5 years from now, you may see that a lot of people are writing code in sickle. Possible. Okay. And they are having 3 major vendors who are there. CodePlay has recently merged with Intel. Okay, they have been merged. And so you have basically now only 2, okay, Intel and CodePlay together, and then adapt to CPP. And then there are 2 private ones, free ones, Tricycle is available on the GitHub. So you can see that these are already implemented. So Intel one, for example, already shows to work on AMD, NVIDIA, and Intel GPUs. So it's already runs on all of them. And for specific cards, they have some drivers or some tools, that toolkit that is required, and I will just mention that here. So okay, here, so that one API for NVIDIA, one API for AMD, that is required, and that is available such that on AMD the MI series of cards can be supported immediately. On NVIDIA, I think A100 onwards it is supported, so that is readily available. And sickle, SYCL is pronounced as sickle. Okay, SYCL sickle, and it is basically promising you that it is a ISO C++ code, and it will offload the work to processors. Okay, so it will do it automatically. And it has the ecosystem. Right now, the C language, LLVM, all of them are supporting, and therefore they are now available for various hardware platforms. Okay. So we are using one API because Intel has made one API for free, and it runs very fast on Intel hardware, and we have Intel hardware. So we are running on one API, and we can start taking advantage of that. So it does a pretty good job. One API runs very nice. Okay. So earlier Intel had separate compilers for C, C++, Fortran, and they used to sell, etc. Now they have put everything under one API, and they made one API free. Okay, so it's very big boost for us to write codes. Okay, so that's all. So I stop here. If you have any questions, you can ask me. What is going to follow? Today is actually a little bit packed. We are going to have 2 tasks. One is one API OpenCL solver, and the other is post-processing. So we will take post-processing towards the end, and we will have some demo followed by discussions of installation running with our volunteers after me. I think maybe we'll take some 10 minutes break if there's a tea. Yeah, we'll take about 15 minutes break and then come back. And then we'll continue with the installation. We will have 2 ways of installation. We will have a simpler installation with drivers. 3-line installation is possible for us. We will do that. And we'll also make a singularity image available for you shortly. Okay, we ran into one small issue. We will clear it up, and then we'll make that available. And then that will complete the singularity images for all the solvers of MicroSim. Okay, but luckily for OpenCL, even without that, the dependencies are only very few. So you can already start to try out here. And because it will run on every CPU, all of you can actually install and run it. Okay, so that is also an advantage. We will do that after the break. Okay, thank you. So some of you who want to buy some computer, etc., please remember, one of the largest number of cores are available for a desktop processor. AMD Ryzen has what is called Threadripper mode. Okay, that will have an enormous number of cores available. And then AMD, Epic series of processors also is available with 128 cores, 192. So which means that if you buy one desktop with one CPU, you already have a supercomputer with you, practically. Okay, so you don't need to worry. With just few lakhs, you have ability to run these codes. Okay, and our code will run on those very peacefully. The GP solver, the open form based solver, and OpenCL based solver will run on these machines very peacefully.